So we're going to start learning about the next kind of thing, and that's transformers. Not the kind of transformers that are the big car robots that walk around and terrorize cities. No, we're talking about this kind of transformer.
Tanner, Tech, Tanner, Tech, Tanner, Tanner, Tech, Tanner, Tech, Tanner. Hello, this is Tanner Tech.
And today, I'm going to be teaching an electronics class. So, the vice principal of my high school has recently asked me if I wanted to teach an electronics class. And, of course, I wanted to do this a lot. So, I volunteered and I did this electronics class. So, in these next few videos, I'm going to be doing the different days of my electronics class. And mostly, it is me lecturing at the whiteboard on how different electronic components work and how electricity works. I will then put some clips of me teaching these students how to etch and make their own circuit boards from scratch. Because we did that too. I was able to help them design their own circuit that did a certain purpose, and then build that circuit board on a breadboard first, and then build it on a piece of copper clapboard. So in this video, the first video, is just going to be me lecturing. In the second video, it's probably going to be me lecturing too. And then in the third video is going to be the experiments I showed these kids about how to build their stuff. So in this electronics class, I had about 9 people, ranging from grades 7 to already graduated, and they all went to my same middle school / high school. And it was a pretty cool class because I was able to teach these kids all about electronics. I also brought half my lab over here. But it was an awesome class to teach, and it was pretty fun. So if you have ever wanted to learn about electronics, but didn't really know how, I'm probably going to make videos in the future explaining different electronic components, but these videos would probably be pretty short. But this one is just a wide video overview of my lecture of electronics, which is pretty interesting to watch. So if you want to watch a whole lecture about this, you can watch this. But if you want to watch smaller videos that show more about each individual part, then you can watch some of my future videos that come up. So now, to my lecturing. Electricity is awesome. It runs our cell phones, it runs our cars, it runs our microwaves, it runs everything in daily life. Imagine what it would be like if we didn't have electricity. We wouldn't be able to turn on the lights, we wouldn't have air conditioning. This room would probably be super hot right now. There'd be so many things you'd be missing out on if it weren't for electricity. But a lot of people don't really know exactly how electricity works or how it functions. So in this class I'm going to be teaching you how electricity works and how it can work together to make all the devices in your daily life work. So, many of you don't know me, but I have studied electronics by myself, and I build these things. Like this high voltage power supply that I was showing you guys earlier, I built this from scratch. I designed this circuit board right here, and I built it. And it's taken me about 4 years to learn all these electronic components and how they work, because they're pretty complicated. I'm going to try and teach you guys in 4 days. So, to get started, I'm just going to show you this high voltage power supply, because it's one of the cooler parts of electronics. I'm also going to bring my Tesla coil tomorrow, which is one of those things you see in movies that shoot blue lightning bolts everywhere. So if I turn this on, you can see an electric arc. And it's pretty cool. And that is electricity flowing. So that brings me to my first point that I'm going to get started on, how electricity works. So many of you guys have heard voltage and current. Those are the two main characteristics of electricity. So if we look at the wall right here, this has 120 volts. Now, a lot of people don't know exactly what volts are, so here's what it is. So imagine on a battery, there are, first let me get a better example. So if we have a battery has 2 points on it. It has a positive end and a negative end. Now, between these two ends, there's about 1.5 volts in most AA batteries. So that voltage is electrons. So how many of you guys know what electrons are? Okay, so electrons are parts of an atom, and they're these tiny little parts, and they can move around inside metal, and those are what forms electricity. So inside a battery, we have two wires coming out of each end, and these wires have different amounts of electrons inside it. The negative end is going to have tons and tons of electrons inside it, and the positive end is going to have just a few electrons inside it. Now, the difference in these electrons in each side is the voltage. So if we have a 1.5 volt battery, then there's going to be quite a bit of electrons on this side, and there's going to be quite a bit of electrons on this side. And so when there's a difference in electrons between 2 points, that means the electrons want to get over to the other side. So do you think these electrons will want to get to this side? Now, how do you think they're going to get there? Because they've got to get there somewhere. Because inside, oh yeah, go ahead.
They're going to travel through the metal current? Yeah.
Awesome. You got it right. So there's a chemical reaction inside the battery that's formed with two metal plates and some acid inside. And that causes the electrons to migrate over to the side. But they want to get back. And like he was saying, they have to go somewhere. And so they flow through whatever circuit you have hooked up to here, whether it be a light bulb or a motor or an iPhone, and they power it. So these electrons want to get here really fast. Now in the case of a 1.5 volt battery or something small, the electrons don't really want to get there as fast, and so when they flow through here, they move relatively slow to get through. But if you take something like this is about 35,000 volts. So this is way higher than that. And so as you can see, most electrons can barely travel through metal because they're going so slow. But these electrons that are traveling through the circuit go so fast that they're able to jump through air and travel through air and make air into a conductor, like this. So this is kind of how basic electricity works. We have a lot of electrons on the cathode, or the negative part, or ground. And those electrons flow through the circuit to here. But something is kind of weird about electricity, or electronics, and that's the way the current flows. So you may think the current is flowing from the negative to the positive because there's a lot of electrons, and that's the way the electrons are flowing. But that's not actually the way that the current flows. So in most electronic circuits, to make it easier, you just think of it that the current is flowing from the positive through the circuit element and back to ground. Now that's the opposite way the electrons are flowing. So just remember this. It's pretty easy. Well, kind of. So just remember the electrons are flowing the opposite way the current is flowing. The current is flowing positive to negative. So you don't really need to know much about electrons anymore because we are mostly going to be just thinking about the circuit flow. Any questions about that part?
So, current, it's the opposite way that the electrons are flowing.
Yeah.
So, why is it? Why?
Well, I'll get to that later in the class when I explain transistors and diodes and different things that show current. But the reason that current flows in the opposite direction of electrons is pretty much to make it easier for anybody who's reading a schematic diagram.
Oh, okay.
Because it's kind of hard to think of electronics. Because let's take, for instance, a transistor. And I'll explain these later in the class. But this is the circuit diagram for a transistor. And the current flows through this part, or this leg of the transistor, and out this leg. And so this little arrow makes it easy to know where the current is flowing. But if we had the electrons going this way through the circuit, it would be kind of hard to understand because the electrons are going opposite of the arrow. So circuits are a lot easier to read and understand when you realize that the current is flowing the opposite way of the electrons.
Okay. So it's like a classification thing. It's not like an actual
Yeah.
Yeah. Okay.
It's like a visual aid.
Yeah.
So that is voltage. Voltage is the potential difference of electrons. So there's a lot more electrons on one end of here than on one end of a AA battery. There's a lot more electrons on the wall voltage, because that's 120 volts in here. But now I'm going to explain current. Current is how many electrons are flowing through one certain point of a device. So for instance, if we take this circuit, for example, and we see the electrons are flowing through here to get through the light bulb and back to ground. Now, current is how many electrons are flowing through this one point at one time. So, you know what? I'm going to explain this in an easier way, and that's with this water bottle. So, if we think of a high voltage source, then we can raise the water bottle up, because the higher the voltage, the more the electrons want to get back to ground. This is figurative ground. So if I put this water bottle here, do you think that water is going to go very fast when it's hitting the ground there? No? But if I move it way up here, it's going to go really fast. So if I open this up, and I put it down here, the water's coming out, but it's not going very fast when it hits down here. But if I move it way up here, then when the water hits the ground, it's going pretty fast. So this is like a high voltage source, and that is like ground. So we can think of different electronic currents as how much water is flowing. So in this example, you see right here, there's not very much water flowing. And you can think of the water like the electrons. But if I were to take the cap off this water bottle and let tons of electrons flow out of this, this is like a super high current source, because you can see there's tons of electrons flowing out of this water bottle. So that's kind of how electric current, electric voltage works. We can see that voltage is how fast the electrons go, and the difference in electrons in 2 points. Current is how fast the electrons are flowing. So current depends on what kind of device you're using. So some devices use higher current than others. Like, you know how you see light bulbs, and some of them say 60 watts, some of them say 30 watts. Well, those light bulbs still use the same 120 volts source, but they use different amounts of current. So one light bulb that's running off the wall, the 60 watt light bulb, is going to have a lot more electrons flowing through it at one time than the 30 watt light bulb. And we can kind of figure this out using something called Ohm's Law. But I'm going to get into that after I explain alternating current. So here I explained that the current flows through the circuit in one direction here. It flows from positive to negative. But that is called DC current, direct current. This means the current is flowing in one direction through the light bulb and back to ground. But there's a different kind of electricity that's pretty cool. And it's the kind of electricity that comes out of all of your walls. Because direct current is used in your phone, it's used in batteries, it's used in some power supplies. But alternating current is when you switch the positive and the negative terminals. So let's say this is positive first, and this is negative, and the current is flowing through this way. But then we'll switch that, and we'll make this negative and this positive. And the current starts flowing the opposite direction. Now imagine that changed 60 times per second. That would be fast, huh? Well, that's how much the wall is switching. It's switching from positive to negative 60 times per second. And we can see this AC voltage on something called an oscilloscope, which is this thing right here. Now, I bet you guys have all been wondering what this is, because it's this fancy mad scientist invention that's sitting right here on my desk, and it has all these millions of knobs and this cool little screen. Well, this thing is called an oscilloscope, and it measures voltage over time. I guess, have you all guys all been in math and drawing graphs and stuff, right? So, you haven't? Or? Oh, okay, sorry. You're nodding your head, like no. Okay, so on a graph, we know that there's a y-axis and an x-axis. So this oscilloscope graphs for you, but it graphs voltage, which is the y-axis, over time, which is the x-axis. And you can change how big these axes are. You can make the x-axis, which is time, you can make it 1 second, 2 second, 3 second. Or you can even make it 1 microsecond, 2 microseconds. Microseconds are so fast, there's billions of them in 1 second. You can make this voltage from 30 millivolts to 20 volt, to 50 volts per division. So that's kind of how an oscilloscope works. And it has this little beam, and I'll explain this later when I explain vacuum tubes. But it has this little beam that shoots at the screen. And pretend this beam is my hand. The oscilloscope will graph this beam kind of like this to graph the current coming from the wall. So let's fire this thing up and see what it does. You guys, if you want to see it closer, you can come up here and I'll show you. But it takes a little bit to warm up. And once it does, you can see that there's this little line tracing across the screen. Now this line is the voltage over time graph. And so we can see the alternating current if I connect this to one of my wall voltage sources. To use that, I'll just connect it with this cable. So if I plug this thing in, these things always get stuck. I'll plug this scope, and what I'll do is I'll set it to the highest voltage setting there is. Because if I set it to too much voltage, I'll burn out my oscilloscope. And I'll also set this to alternating current. And then when I connect this up to my wall source, you can see a little sine wave on there. Let me just stick that in. So this sine wave is what the alternating current coming from the wall is. So as you can see right here, the voltage when it's up here is the 120 volts that comes out of the wall. But then the voltage changes. It goes to negative, and that's negative. So these two little poles on the wall right here are constantly switching from positive to negative in this little fashion, which is pretty cool because that allows you to transmit voltages for longer distances, and it allows you to use something called a transformer, which I'll also explain later, to step these voltages to varying different levels. So that way you can have voltages go from 120 volts through this thing called a transformer down to 40 volts. And this thing turns that 40 volts DC into 35,000 volts AC through this transformer. So we can see the difference between DC and AC if I hook up my next probe and I connect it to this power supply. So this power supply right here is DC. So I'll connect my oscilloscope to this DC power supply. It's not working. So I'll connect my power supply to this DC power supply, and we can see that it will have one solid line going up. Just a second. And if I turn it down, you can see that this little line is going straight up here like that. That means that this voltage is constant. Because like I said, there's a graph right here, and it graphs voltage over time. Now because it's a DC power supply, the electrons are always going through the circuit one way. There's always tons of electrons on the negative end. Sorry, I switched them around. But in the alternating current power supply of the wire, the electrons are constantly moving from this end to this end, back to this end. And so if we look at the voltage over time graph on the oscilloscope right now, that's DC. So the voltage is staying constant over time. It's not changing. But if we look back at that AC voltage that I showed you before, we can see that the voltage is always changing to make this little sine wave type thing. So the voltage on here is changing from positive to positive to negative, many times a second. So that's pretty much how AC works. And that's the difference between AC and DC. Now that's only 60 times per second. Now there's a lot higher things. Some things like your Wi-Fi router, that has electricity and it pushes back and forth billions of times per second to make your Wi-Fi signal work. So I'll turn this off and I'll start talking about Ohm's Law. So Ohm was this guy who lived a long time ago, and he figured out something that works in electricity. And he figured out how resistors work.
Depends on how much resistance.
Yeah, so there's a whole color code that you can know from these resistors to understand how they work. And that's kind of a little bit difficult to explain, so I'll pull up a picture of one in just a second. But pretty much, you see those little lines on the resistors, the little cylinders? Well, those lines tell you how many ohms there are. So the first line, the first and second line, tell you the first two digits of the resistance. So for instance, red would be 0, no, brown would be 0, black would be 1, red would be 2, and then so on through the rainbow. So if we have a resistor that has the first line being red, the second line being brown, the third line being black, and the fourth line being black, then we could calculate the value of this resistor. Because the first one is going to be red, and that's 2. And then we have 0, we have 1, and we have 1. That means it's 201 ohms, and the multiplier is 1. So that's 201 ohms total. But if we made this like yellow, which I think was 6, then the multiplier would be, I think 1,000. No, however many zeros are there, so it's going to be a lot. But anyway, that's kind of how the resistor color code works. And I'll show you a chart that makes this a whole lot easier than how I just explained it right now. So if you guys want to come up here, we can play with some resistors, and you can kind of understand how they work. So come on up. So this is a multimeter. And pretty much what a multimeter does is it measures resistance. And it can measure a lot of other things. So you guys can use this, and I'm going to go grab another one. And you can play with the resistors, and you can play with this power supply to make a kind of circuit like this. So let me go get some scissors to open this thing up, because it will not open. So let's say you took a 2K ohm resistor and you put two of them together on this 12-volt power supply. If they're the same resistors on here, then you're going to get half the voltage you begin with. So if someone wants to take this power supply and connect two of these resistors together, then read the voltage. It's pretty cool what you'll be able to see. You can also use this power supply to read the voltage. So if we take these two things right here, and we touch them to these two probes right here, we can see that we have 13.6 volts, which is close enough to 12. So you can play with this, and you can play with these resistors to see how they react to this. So anyone who wants to, just go ahead. I'll help you around. You're not going to get hurt, by the way. There's a common misconception that electricity is super dangerous, and it is. Like, this power supply could kill you if you touch these two things together. But there's a lot of other parts of electricity that are dangerous. Like this 12 volts. Some people think electricity is dangerous. I'm touching both sides. I'm fine. So pretty much what that comes down to is that your skin has different resistances, and at different voltages, you'll have different currents because of Ohm's Law. So go ahead, just have fun with these resistors. Hook them up to this thing. Anyone? So right now it's set on voltage, and you can see that it's 5 volts, even through that big resistor. Now the reason it's 5 volts, even though it's going through the resistor, is because there's no current flowing through here. This multimeter just measures voltage. But if you want to see the current that's going through here, we can take this part out, this little red part. We can switch this to milliamps right here, and you can connect it. It's 3 volts. That means that it
Jump down from 6.
Yep, from 5 volts to 3 volts.
Oh, okay.
So you can use different types of resistors or different values and vary them so you can adjust the voltage at the middle. So resistors are pretty cool for limiting current in a circuit and providing different voltages. Let's see what time is it right now.
So it's like, so the example that comes to mind is, you know, bike headlights?
Yeah?
How they're like 12 volts. I
Yeah.
believe. You could, using resistors, I'm guessing, you could bring that voltage down to 6 to charge a phone or something.
Yeah.
Yeah. That's like when you're riding a bike, you can charge a phone.
Yep.
That's sort of the idea.
Pretty much. But there's easier ways. Resistors are not a very efficient
Way
way
to do
to
that.
step down voltage. I mean, it'll work to get a voltage right here, but if you do that, then it's going to waste a lot of power because there's always going to be current flowing through and not your circuit. So that just wastes power. And I'll explain watts in just a second. Because watts is how much power. So if anyone who hasn't like played with these resistors, go right ahead and you can put two resistors together to form this little circuit that I was showing these guys over here that shows how much, it shows current flowing through a circuit like this. Because right here you can see there is, I forgot, there's about 3 volts on this, there's 2.5. So if you take two resistors and you put them together like that, you can get different voltages. So go ahead and try that. Right now, you're putting just straight voltage across here. And if you put it on a tiny resistor, then you can get your resistor to get pretty hot if you use a very small low resistor. Like if you used a 220 ohm resistor and put it on here, then you get a lot of heat dissipation off that resistor. It would get hot. So next we're going to learn about watts. Anyone else want to do this right now? No?
Do you want to?
I was going to ask a question. So resistors, so they don't like slow it down, they just cut it in half basically, or like cut little parts off.
Well, kind of. Let me explain that better.
If you said waste.
Yeah. So what happens is the electrons, when they're going through this circuit and they go through the resistor, they'll bounce around inside the resistor. And that's how it slows the electrons down. Now, when they bounce around inside this resistor, they're going to hit it. And that's going to create heat because there's electrons getting lost inside here, getting slowed down. And that lost power, that lost speed of the electrons has to go somewhere. And so because they're running into the sides of this resistor, it's going to heat up and get pretty hot. Some resistors even get so hot as to make it so you get burnt. Okay, we're going to take a quick break right now, so if you want to go get a drink or something. Because I used my water bottle for there. So we'll take a quick break and we'll meet back here in like 5 or 6 minutes. Okay, so next we're going to talk about wattage. Now, wattage is, like I was talking to you about the heat being lost. So if we look up here and we see a resistor, and it's 50 ohms. Now, if there's 10 volts and there's 50 ohms, we figured out there was going to be 0.2 amps, right? Now, the formula for wattage is wattage equals voltage times current, or E times I. Now, wattage is kind of like when you see a 60-watt light bulb, a 30-watt light bulb, and you see that's how much power it takes. Now, power is the voltage multiplied by current. So we have how many electrons are going through the circuit by how fast those electrons are going to go at a certain power. And we can see like how much wattage is flowing through a circuit if we just measure the current and measure the voltage. Now if we take a small resistor like this one and we hook it straight up to the power supply, we can see how much wattage is being lost. Because let's take a 220 ohm resistor, for example, and we're going to run it off a 12 volt power supply. So if we take E, which is 12, I, which is unknown, and then R, which is 220 ohms, and we divide 12 by 220, we're going to get, sorry, I can't calculate that number in my head. We're going to get approximately 0.05 watts. So that means it's going to be 0.05 watts of heat being dissipated if I hook this resistor up to that power supply. But if we hook up a smaller value resistor, then you'll see that that current, oh, actually never mind. So that's how much current's going to be flowing through the circuit. So we multiplied 0.05, which is how much current is flowing through a 220 ohm resistor, by 12 to get how much wattage. Sorry, I forgot about that most important spot. So that's going to be 0.65 watts flowing through this circuit because we have a 220 ohm resistor. Now, if you look at these resistor packages, you see that it says 1/4 watt on here. And so that's how much heat these resistors can dissipate because there's that much current flowing through and that many electrons bouncing around in the resistor to make heat. And so if we put over 1/4 watt into this resistor, then it will get hot and it might catch on fire. So we're going to hook that up to see what happens to this resistor. So if I hook this little resistor up, it will start dissipating heat. And as you can feel, or as I can feel right here, it's already starting to get hot. So if I leave this here, it's going to eventually start to smoke because it's dissipating heat. So if I feel it, it's too hot to touch. And that's because all these electrons are bouncing around inside this resistor. And they're bouncing around so fast, and there's so many electrons bouncing around inside there, because there's a lot of current flowing through the circuit. And because it's 12 volts, they're flowing super fast. And all those bouncing around electrons are causing this resistor to heat up and become almost too hot to touch. So in a light bulb is basically a resistor. And so if we have the light bulbs like the old-fashioned ones that have a little filament inside them, those light bulbs are resistors. And when the electrons bounce around inside those light bulbs, they don't just create heat, they also create light. Because they bounce so hard into the side of that material in the filament of the light bulb that it causes light to be created. And so that's kind of a light bulb. So far, we've learned about resistors, about Ohm's Law, about wattage. Any questions about any of this stuff that we've learned? Any questions? You guys pretty much get Ohm's Law, watts, resistors, current, voltage, everything about that? Awesome. You guys are a smart bunch. So we're going to start learning about the next kind of thing, and that's transformers. Not the kind of transformers that are the big car robots that walk around and terrorize cities. No. We're talking about this kind of transformer. Now, these transformers are cool because they can convert voltages to different kinds of things. And I'll bring my coolest example of a transformer tomorrow in the form of a testing board. You guys ever watched like a Frankenstein movie or any kind of movie where there's a mad scientist lab? Or on YouTube probably. And you see this big tower and it shoots purple lightning bolts out in every direction. That's a Tesla coil and that's a big transformer. I'm going to bring mine tomorrow to show you guys. But anyway, how a transformer works is it only uses AC voltage. And so first, to understand a transformer, we need to understand magnets. Magnets are a vital part of electricity. And have many of you guys ever done that experiment where you take a nail and you wrap a piece of wire around it, and then you can use it to pick up paper clips? You guys ever done that? No?
Not personally.
Okay,
I've
well,
seen it.
I should have brought wire to do that. I'll make a wire to do that tomorrow. But anyway, what happens is when current flows through a wire, and let's just say this is a straight wire hooked up to 12 volts, because that's a pretty useful measurement, and the ground, we know that there's going to be electrons flowing through this. We know the current is going to be flowing through this pretty fast. Now, the cool thing about electricity is that it always creates a magnetic field. And so a magnetic field is going to be going around this wire in this little circle like this. It's going to be going in almost a complete circle around it. Now, magnets, like the magnets on your fridge, are always static. They have one field. if we see that horseshoe magnet that many people use in science classes and stuff, this horseshoe magnet has two poles right here. And those poles are north and those poles are south. Now this means there's the magnetic field lines coming around these poles. And these field lines are showing where the magnetic field is going. Now this magnetic field is also going around this wire whenever there's current flowing through. And if it's just one singular wire, there's not very much magnetic field being created because there's just one wire and it's going around this whole side. But what if you took this wire and you took it and you coiled it around tons of times and made it come back out? Then all the wire, there'd be multiple wires with these little lines going around them. And they'd all be lining up to create this super strong magnetic field around its core, or this little wire. And this magnetic field is pretty strong. And so if you were to take this coil and wrap it around a nail, then what it would do is it would create two ends, a north and a south. So that's how, in some experiments, people are able to do this thing right here and touch paper clips to each end and they stick like a fridge magnet. And if you take the power out of this, there's no more magnetic field. Because when there's power flowing through, the current is flowing through these wires and it's causing these little lines to go through like this. And these magnetic field lines are causing the magnetic field to go through metal. Because magnetic fields are this weird thing, and they flow through air, but not very well. And they flow through metal a lot better, but not all metals. Only metals called ferrous metals, which contain iron. Like magnetic fields do not go through aluminum very well at all. They mostly go through iron. So if we have this iron bar, and there's these currents flowing through these wires, and they cause a big magnetic field around this magnet right here. Now this magnetic field is going only one direction right now because it has a DC current going through. The current is flowing through here and coming out the other side. It's only going one way. But what if we changed this into an AC current like I was showing you on the oscilloscope, where it's changing from positive to negative lots of times? Well, that will make this coil make a magnetic field that's always changing. The magnetic field will get bigger and bigger and bigger as the electricity gets more positive. And then as it starts going down, the magnetic field is going to collapse and it's going to get smaller and smaller and smaller until it's almost gone and it's at zero. Now that small magnetic field is then going to go into the negative end. It's going to switch from this to negative, and the magnetic field is going to go the opposite direction. So that changing magnetic field is not going to be good for picking up paper clips because if it's always changing directions, you won't ever be able to pick up anything with it. But it is really useful for transformers. So transformers, like this one that you see right here, is a combination of two different coils like this, surrounding an iron core. So iron is what makes up nails, it's what makes up everything. And this core is made of iron too. And so we have this iron core in the shape of two E's. So I'll draw it right here. Wait. This iron core, let me get a new marker. This one's not. Okay, this iron core looks like two E's put together. And what happens is if you are able to take this and you wrap a coil of wire around each part of the core. Like if you wrap a big coil of wire right here, and you wrap a big coil of wire right here, and you put a changing magnetic field through this coil, like the AC current right here, and it's going to make the magnetic field flow through this E, through this side, and back here, and through this E, through this side, and back here. And what's going to happen is that it's going to change directions because it's the AC voltage, which is constantly going from negative to positive. So the magnetic field is constantly going to be changing inside here through this coil. Now, the cool thing about this is this changing magnetic field can make current flow inside another coil. Just like putting electricity through this coil makes a magnetic field, you can convert that magnetic field back to electricity inside this coil. And so that way you can change the different voltages. So this all depends on coil windings. So let's say I have a coil on one side of this transformer, and this coil has 200 windings. Now if we have this coil right here, let's say this coil has 50 windings. Now if we take those two coil ratios, and I think you guys all know about ratios and stuff, right? So that would be 200 to 50, which would be 4 to 1. So what we can do with that is we can see the different voltages this transformer is going to create. So if I put, let's say, 110 volts into this side of the transformer, into this coil right here, and that has to be alternating current, like from this wall. And then we measure the output voltage of this one. It's going to be that divided by 4, which is going to be 27.5 volts. So this is going to be putting out 27.5 volts. And this is going to be inputting 110 volts. And so you can see it's pretty cool because you can use the transformers with different amounts of coils on each side to actually create different voltages coming out. So it's a really awesome concept. And this was invented by a man named Nikola Tesla back in 18-something. And he realized that you could use these different transformers to step up voltages to make different amounts of voltages to go different places. Like some things, they can't use too high of a voltage. Like if you have your phone and you try to charge this phone on 110 volts, that's going to explode your phone. But different things like a light bulb, if you try to run your light bulb off 5 volts from your phone charger, your light bulb's not going to light. So these transformers are able to convert these different voltages so that way everything can be powered by its correct operating voltage. Now those power lines outside, those power lines need a super high voltage. Because if you have a low voltage going through a power line, it's going to lose power pretty fast because the electrons are going slow. And so if you have a power plant, like the one in San Onofre, 200 miles away, then that power is going to be really small by the time it reaches. Because even though those power lines are conductors and they're made of copper, they're going to run out of electricity because the electrons are going to be bouncing around. And so these transformers step up the power on those power plants from the low voltages that the nuclear reactors create to super high voltages that can flow through the power lines without losing much voltage. And have you guys ever been driving by those power plants? I mean the power conversion stations. I think there's like 2 or 3 of them in heaven. But you see all these different poles and you see all those metal boxes and it's surrounded by a big barbed wire fence. You guys ever seen those things?
Yeah.
Well, pretty much what those do is they step down the high voltage that come from the big power lines into a slightly lower voltage. So, believe it or not, the voltage flowing through those big power lines in the desert and stuff, 115,000 volts. That's like 4 times as much as this power supply, so that's a lot. Now those get stepped down in those big power conversion stations that you see into 2,000 volts, which goes in the power lines that go around our city. Those get stepped down at your house to 110 volts that you use in all your walls. So that voltage is what comes out of here. If I were to take my multimeter and just plug it straight into the wall, and I wouldn't advise you do this at home, but it is actually safe, then we can see that the voltage on here is going to be 117 volts. Now, you guys can all see this. This voltage changes sometimes because the power plants aren't always the same. And sometimes they put out more power than others. But right now it's going 117 volts AC. And now, this transformer on my power supply is a transformer that steps that 117 volts down to 40 volts to power this circuit right here. And so we have a coil on top that is some amount of turns. Now I'm not exactly sure how many amount of turns are on there, because they can change this ratio of turns tons of times to different amounts and still get the same voltage out. So this transformer steps down to 40 volts. So there's a certain ratio of turns, because we know there's 120 volts here and 40 volts here, and so we can calculate the ratio of those turns. Now this transformer is a cool one. This transformer steps up 40 volts to 35,000 volts. And so we have thousands of turns on one side, and we have 5 turns on this side. And so we can calculate the amount. Watts equals voltage times current. Now, if we have a transformer that has 110 volts in, it's going to have the same wattage on the output, but not necessarily the same voltage. So if we have a transformer that has 100 watts going in at 100 volts, just to make it easy, then this transformer is still going to have 100 watts coming out. So we have 100 watts, 100 volts going in. And let's say we have 50 volts coming out, 50 volts. And we're still going to have 100 watts, because we're not amplifying anything. We're not giving it more wattage. Just like those dumb free energy machines you see on YouTube that say they can make free electricity. Those are all, they're garbage. So when something has wattage coming in, it's going to have the exact same wattage coming out. But the transformer changes the voltage, which means it's also going to change the current flowing through. So if we have 100 watts at 100 volts, that means there's going to be 1 amp flowing in. And then we have 100 watts at 50 volts. That means it's going to be 2 amps coming out. Because there's this thing called conservation of energy. And we can't create energy from nothing. So it's always going to have about the same wattage going in as the same wattage going out. Because it may be slightly lower, like maybe 90 watts, because the transformer kind of heats up, because no transformer is perfect, so there's going to be some loss of electricity from electrons bumping into the walls. Any other questions about transformers?
Is that the better way to make the bike charger?
No.
No. Okay.
To make your bike charger,
Yeah.
we're going to use something called the switch mode power supply.
Okay.
And I'll explain that later. Because using a switch mode power supply, that uses inductors and transformers and diodes and all kinds of things. Okay, so I think we kind of understand transformers, and we kind of understand AC, and we kind of understand basic electricity. So now we're going to go into something called semiconductors. Semiconductors are pretty cool. They are what are able to make transistors work, they make your phone work, they let the memory inside your phone work good. They let things change AC to DC. Semiconductors are like what makes our lives possible right now. So, first of all, before I go into semiconductors like diodes and transistors, I'm going to go into the really old-fashioned equivalent, which are vacuum tubes. And vacuum tubes are kind of easier to understand because you can visualize the electron flowing through it. So, let's take a look at a simple vacuum tube diode. Now, this is going to only let electrons flow through one way. I wasn't planning on talking about this yet today, I was just planning on talking tomorrow, so I haven't brought any diodes today. But I'll bring some tomorrow to show you guys. So on the vacuum tube diode, we have this thing called a heater. And pretty much what a heater does is you have a current flowing through it. It's kind of like a little light bulb socket. And this is going to make the electrons inside bounce around, because this heater is like a little resistor. Now when these electrons bounce around, this heater is made out of a special material, so that way when the electrons bounce around inside that little heater, they eventually fly out, they get loose. So it's, these little electrons are flying around everywhere, so it's making this little cloud of electrons around here. Now if we have this top plate right here, and this bottom plate around here, and these two plates are different. This plate is being hot because there's tons of electrons, and this plate is cold. And then we apply a negative voltage to here, and a positive voltage to here. That means we're going to be giving this side tons of electrons, and this side not very many. And because there's a vacuum, and there used to be air molecules inside here, but with those air molecules gone, these electrons are able to shoot up like a gun and shoot up to this little anode right here to cause current to flow. Now the cool thing is, if we switch this and we made this side instead negative and this side positive, then no electrons would flow because there's no electrons flowing around this end. And so even though there's tons of electrons right here, they have no way to get to this because they're not bouncing around because they're not hot. So in this circuit, the electrons can only flow in one direction. They can't flow backwards. And this is super useful for converting different types of electricity. Because if we were to take this AC voltage that's coming out of the wall, and we want to use that to charge our phone, that voltage is going to be changing constantly. And so there'd be no way for it to charge your phone, because for every time it switches from positive to negative, it's going to be charging our phone and then discharging our phone. And so it's not going to get anywhere. So we have to make it that DC voltage that I was showing you that came from this power supply. And so in the vacuum tube example, if I have the AC voltage coming in this direction, the AC voltage is coming in here, and it goes through this wire. When it's in its negative half of the voltage, then the electrons will be able to flow through this way. But when it goes into the positive half of the voltage, and this is positive and this is negative, no electrons are going to be able to flow through. So from this, we can see that in this vacuum tube example, the electrons are only able to flow through if this side is negative and this side is positive. So that pretty much makes it so it kills and cancels out this bottom half of the electricity. So we only have this top half. And so that means the electricity is only going on and then off and then on and off. So never going negative. And so that's kind of a DC voltage. And I'll explain how you can get this rippling DC voltage into a smooth DC voltage with capacitors later. But anyway, this is a vacuum tube. Now to the modern equivalent of a vacuum tube, which is a diode. Now this is only a diode vacuum tube. There's also triodes, which I'll show you how it relates to a transistor. A diode symbol looks something like this. It's a little arrow, and it has a little light on it. And pretty much what this arrow or diode is able to do is it only lets the current flow through this diode in one way. Now remember how before I was telling you how the electron flow and the current flow are a lot different from each other, because one flows one way, one flows the other way. Now if you think of current flow, current is only able to flow through the diode this way in the direction of the arrow. But if we think of the electron flow, the electrons are only able to flow backwards through the arrow. And that doesn't really make sense. So that's kind of why we use current instead of electron flow in our circuit diagrams for electronics. So right here, if we have the current flowing this way, we have all the electrons trying to get through this way. They'll be able to go through. It's kind of like a one-way valve. But if we have the electrons trying to go through the opposite way, they're going to get stopped. And they're not going to be able to go through this diode at all. So they're going to get stuck here. And they're not going to be able to move at all. So these diodes can be used for all kinds of things. Like if you wanted to convert that AC voltage to DC voltage, you could do that with diodes, because those only let electrons flow in one way. They can also be used to protect something. Like if there was a device that you could plug in backwards into a DC voltage, that if you plugged it in backwards, it would fry it out. These diodes would be able to make sure you could never plug something in backwards, because if you plugged it in backwards, then the electricity would just flow through the diode and not go through at all. It's kind of hard to explain. Anyway, diodes are one of the most widely used electronic components because they can be used for almost anything. And there's many different kinds of diodes, and I'll go into those later tomorrow when I go over semiconductors. So tomorrow we're also going to go through transistors and how those work. Now transistors are awesome because they're able to let you amplify things like you were talking about to make a smaller electric voltage higher. And I'll bring in some of my custom vacuum tube amplifiers like for guitars to show you how to do that. But anyway, this class is almost over for today. And we went over a lot of main concepts. So do you guys have any ideas for any electronics projects you want to do? Because I think for the last day, I'm going to bring in my soldering iron and some components. I'm going to help you guys build your own little electronics projects. So is there anything you guys want to do? Yeah?
A tiny little solar panel to charge your phone.
A solar panel to charge your phone. We can do that. So we have this big solar panel up here, actually, and the solar panel puts out a pretty high voltage. And so, for your project, we can build a supply that will convert the 12 volts or higher from the solar panel into a voltage enough to charge your phone. So we'll do that for your project. Or if anyone else wants to join that project, they can. Anyone else that want to build anything else? Because I'll need to know so I can get supplies for those things. Huh?
I don't have a bike.
I don't think we can build a bike.
Yeah, I know. Well, no, I mean like a bike that when you ride it, it charges your phone.
Oh yeah.
Yeah.
So, is there anything else like we can build high voltage power supplies like this thing? We can build almost anything, and I'll help you guys step by step through anything you want to build. I'll also bring other projects like to build amplifiers and stuff that you guys can build. Have fun there. Yeah.
Little electric car or something?
An electric car. We can build that. I'll see about that. I'll think about it. It'll probably just be an Arduino robot. I'll go over Arduino on one of the days if we have enough time. And then I'll help you program an Arduino robot to make it work.
And I remember you talked with Jacob about like a chip or something that was hot on one end and cold
yeah.
on another.
A Peltier chip.
Yeah.
So those things are pretty cool. They're not widely used in electronics at all.
Okay.
But most refrigerators don't use these, but some of the little tiny ones do. Now a Peltier chip is this little tiny chip that if you put electricity through it, it can make one side super hot and one side super cold. And then if you put heat on one side, it makes electric current, like to charge your phone. So I could bring one of those in and we could play around with it because it's pretty cool. Because it makes your own little personal air conditioner. So I'll bring some things to make amplifiers, like to amplify music from your phone. And we can build one of those from scratch, which is pretty cool. I'll also bring some other stuff to help you guys make different circuits with. So we have about 10 minutes left.
I know what my project was. Can I do like your own? We talked about this where you can like trick your body that you're like being air conditioned by putting it on your wrists or something like that.
I'll bring some chips and you can do that for your projects. Okay. So I'll just bring some other amplifier. I'll bring some other electronic chips and stuff to make amplifiers that you guys can use to make some of your different projects. Yeah?
Wait, by amplifier for your music, do you mean like a speaker?
Yeah. So it's pretty much, we're going to build a circuit from scratch that uses transistors to take the low voltage from your headphone jack in your phone and convert it into a higher voltage at a higher current that is able to drive a speaker so that way you hear it louder. And I'll go over how the circuit theory of that kind of thing works tomorrow. But it'll be pretty cool. Now, we have like 8 minutes left, so I'll go over some of the basics of transistors. Because transistors are awesome. And I'm going to be going into those a lot more tomorrow. But pretty much a transistor, or the circuit symbol for one at least. All these markers are dead. Okay, so this is a transistor circuit diagram. Now there's many different kinds, but this kind of transistor is an NPN BJT, or bipolar junction transistor. Now, what happens is if you have a tiny little current flowing through this end, which means you just have a few electrons just flowing through there, then it's going to turn on the transistor and let a larger amount of electrons flow through this way, through the arrow. So just kind of like this light switch on the wall, if I move my finger just a little bit on this light switch, we can see that it causes lots of current to flow through this light in the classroom. And so the lights, the transistor, is kind of like a little switch. And when you put a tiny current through this part of the transistor, it acts like a big switch to turn on lots of current through here. And so in the speaker amplifier that I was talking about before, if we have the tiny little voltage of this, it's pretty small, this will allow this switch to turn on and off in the same way this little sine wave is turning on and off over here. And so it could allow the voltage to, a lot of voltage and then a little bit, and then a lot, and then a little bit to flow through here. And it creates a huge, bigger sine wave. So you can use a transistor as an amplifier. So there's many different kinds of transistors. This is only one tiny kind. If I move this arrow right here, over to here, then we get a PNP transistor. If I draw another transistor, kind of like this, this is a metal oxide field effect transistor, and I'll explain these more in detail tomorrow. But transistors are so much to learn about them. And they're so cool because you can use them to do almost anything. Now transistors, and all these things about electricity that I've been talking about, their main purpose is to bend electricity. So when I think of electronics, I think of it like you're able to bend electronics to your will to do everything you want to do. And that's what interests me so much about electronics. And that's why I did this class, because I'm hoping to interest all of you. Because the coolest thing about this is, if you have something that you want to do with electronics, but you don't see that part or you don't see that device in the store, and you don't want to pay a lot for it, you can build it yourself. And it's just so cool to know that you mastered the ability to bend electricity to your own will. It's kind of like a superpower, knowing how to do these electronic components. So when we take a look at this board right here, then this little circuit board right here, I was able to come up with a design for this circuit board and build it so that way it can bend the electricity from the wall to a higher voltage. And so I'll be showing you how to design circuit boards like this too. They're pretty cool. I'll bring in some circuit parts and you'll be able to draw your own circuit boards and make them. But
Iron Man.
Huh?
Iron Man.
Yeah, Iron Man is pretty cool because he makes his own stuff. But this class, I'm just going to be teaching you tomorrow more about electronic theory. And then I think for the last 2 days, I'll bring in more hands-on stuff so we can have a bit more fun, so we can actually build our own circuit boards, and I'll teach you guys kind of how to solder.